Hello and welcome to this clip on rates of reaction to A-level. We'll start by having a look at how we define rate of reaction and a quick review of some of the factors that alter it from GCSE. Then we take the idea of the collision theory that you would have done at GCSE and move it up a little bit and talk about how the orientation of collisions is actually quite critical to the success of the collision and whether the two particles will react. Obviously, if you've been looking at GCSE rates of reaction, it's literally just what causes the rate of reaction to increase, but how we can actually effectively measure the rate of reaction at A-level is very important as well. And not only that, but how we can actually measure the rate of reaction at different stages in the reaction. Not just is it a fast or slow reaction, but how fast is it halfway through as opposed to how fast is it at the beginning. And finally we move on to look at the Boltzmann distribution, which is a graphical way of predicting the proportion of molecules that we think are actually reacting or capable of reacting at any given time. So as always, there will be some definitions that we'll cover as we go through. I'll bring them up in a second. When they do come up, it's a good idea to pause and make sure you've got a flashcard for each one. Go away and make sure you've remembered it and memorized it, because during the course of the clip we'll assume that you have done so. So like I've just mentioned, during the course of this video clip it'll be assumed that you are fully aware or understand the meanings of all of these terms. So it's worthwhile pausing at this point and making sure you've got a flashcard for each one to have handy while we go through the clip. Okay, so let's get stuck in. So at A-level, we don't just say that rate of reaction is how fast a reaction is going. We have to try and quantify a bit what we mean by that. So it's the time taken for a change in concentration to happen. So because change in concentration is measured in moles per decimeter cubed, and the time taken, the standard SI unit for time is seconds, it would obviously be moles per decimeter to the -3 seconds to the -1. This can also be represented graphically. So if we were able to measure the concentration of a product or a reactant at regular intervals, we can produce something called a concentration time graph. And therefore we can take a gradient at any given time to calculate the rate of reaction. So it's quite easy to take the gradient. What you do is you take a tangent. Sorry, let's try it again. And if we were to plot, or work out, the change in y over the change in x, dy or dx, the gradient can be calculated very easily. Like so. So if we look at what dy and dx actually means, it's quite simple really. Dy means the change in concentration of the product, and dx represents the change in time. So this isn't the only type of graph you might get. This is obviously a graph that's charting the concentration of a product because its concentration is increasing as time goes on. If we were to draw the axes again, just sketching them, concentration in moles per decimeter and time in seconds, like we did before, we could have the product graph like that. Try and draw it again actually. And the reactant graph would look like that. So where they cross over, they happen to be in equal quantities. Equal concentrations, in other words. So at any place in either of these curves you can take the gradient and work out what the rate of reaction is with respect to that particular substance at any time. So the next thing to do is to look at the basis of rate of reaction, what affects it and what causes it. So what we talk about at A-level is something called collision theory. This is generally covered quite well at GCSE, and you're probably familiar with the four categories of factors which actually increase the rate of reaction. So what we're looking for is a successful collision. So there's a reason why each of these actually do what they do, and we're going to put those up in a second. But first of all, before we do that, I'd like you to have a think about this and just grab a piece of paper and put down next to each of these factors what you think the reason why it increases the reaction rate is. So the reasons in red are probably ones that you've thought of already, hopefully. I just need to make a quick mention of activation energy. This is actually covered in a separate video to do with enthalpy, but it's relevant to what we're looking at here, so we'll quickly spend a couple of minutes talking about that. So essentially, the energy required to break the bonds in a reactant and get the reaction going is called the activation energy. If we were, however, to use a catalyst, it provides an activation energy that's lower by creating an alternative route that the reaction can take. So there's two actual pathways that can be taken. An uncatalyzed pathway has higher activation energy, so that means that less successful collisions are likely to take place. And a catalyzed pathway has a lower activation energy, so it means that more successful collisions tend to take place. So let's have a look at what we mean by successful collisions. So therefore, the collisions can't just happen, they've got to happen with enough energy for the activation energy to be overcome, and they must also occur in the same orientation. If you try this with your fingers, if you splay your fingers in both hands, and then move your hands towards each other so the fingers interlock, and then move your hands apart, and then move one hand in a slightly different angle, and now try to put your hands together, they won't interlock in the same way because they're not orientated in the correct manner. If you now rearrange your hands so the fingers are splayed out and they face each other, pointing each other, and now move your hands together, the fingers will interlock. So that means they are correctly orientated to react. So it's an analogy perhaps that might help you understand what the idea of orientation means. So for this reason, actually a very, very small number of collisions are actually successful. Most of the collisions in a reaction mixture don't lead to a reaction. Okay, so let's have a slightly quicker look at what a catalyst actually does, just for a few seconds before we move on to one of the other aims in the clip. So an example of a catalyst in real life would be a catalytic converter fitted to the exhaust of a car, which picks up the carbon monoxide, nitrogen oxide gases and unburnt hydrocarbons at the bottom right of the picture from the engine and converts them into the relatively harmless nitrogen, water and carbon dioxide gases that come out the back of the exhaust in the tailpipe that we actually see. These are actually fitted by law and have been since the 1980s across Europe. All cars built and designed and sold in Europe have to have these fitted. It's also worth pointing out before we go on to the next part of the video clip that earlier we said anything which increases the number of successful collisions. It's not just the number of successful collisions on its own, it's actually the frequency of those successful collisions. So you need to make sure that when you're talking about this in exam questions, you always make reference to the frequency of successful collisions. So how many successful collisions are happening per second? So I thought I'd make a reference to that before we go on to the next part of the clip. So don't forget, it's the frequency of successful collisions, not just the fact that there's more of them. It's a very subtle difference between the two ways of saying it. Okay, so let's have a quick look at orientation of collisions and catalysts, like we mentioned before. I've already taken you through the idea of catalysts offering a alternative reaction route of lower activation energy and how to draw that. Now let's look at the orientation, the idea, and also how the catalyst works at atom level. So if we look at what we call a heterogeneous catalyst being in the same state, different state to the reactants. In this animation you have three gases. You have nitrogen and hydrogen reacting together to produce ammonia. That's obviously the Haber process. So the inorganic catalyst is your iron. The iron is used as in a bed. So in other words, it's like on a surface so that the gases can come into contact with it and then be rearranged by the catalyst. So weak bonds form between the catalyst and the reactants. So if we follow the animation as we go, they absorb onto the surface, not absorb, adsorb, and the chemical bonds in them actually break. The catalyst helps this along. The atoms then recombine to form your product, in this case ammonia, and the ammonia escapes. In this second animation showing hydrolysis of a haloalkane, although it's not being catalyzed, if you have a look at the orientation of the OH minus ion coming in from behind, if it was to come in from the other side, the rather large green chlorine atom wouldn't be released as a chloride ion. So it has room from coming in from the left-hand side to undergo the reaction as opposed to coming in from the right-hand side, where it might just harmlessly bounce off and nothing happens. So this graph is called the Boltzmann distribution of molecular energies. It was put forward first by Ludwig Boltzmann, an Austrian chemist, and it was a method for trying to work out or represent the number of molecules with a given energy, and how many of them could actually react. So you can see clearly that it's a bell-shaped curve, slightly skewed, and the activation energy is clearly marked roughly about 65% along. So what happens is, at this point, these are the particles or molecules able to react. You'll notice that it must go through the origin, because no molecules have zero energy. At the same time, it mustn't touch the x-axis, because to do so would imply that that's the limit of the amount of energy any molecule can have. To energy a molecule can possess. So let's just summarize that. So how do you actually make sure your graph that you draw is correct and shows these features? So by making sure that your curve follows those two rules, you can't go far wrong. So this particular graph that you see in front of you at the moment represents a specific temperature. What happens if the conditions change? What happens, for example, if the temperature drops or gets bigger? What happens if a catalyst is introduced into the reaction mixture? It's going to change things slightly. So here we have a graph that shows not only the original temperature, but a higher temperature, T2. The original temperature was T1, the higher temperature is T2, and you can see there's a number of extra particles that can now actually exceed activation energy. The rate of the reaction increases. If you were to introduce a catalyst, here's what you'd do. You'd move the activation energy to the left, signifying that it's actually a bit lower. And this would be EA catalyzed. And what would happen here is no matter what the temperature, you'd now have a greater number of particles that can now react. So this would be particles or molecules that now also exceed EA. So that shows how a Boltzmann distribution can represent how a catalyst affects the rate of reaction, how it now shows that there are more particles that can overcome the activation energy. So what would happen if you didn't have the catalyst and it was colder? It's very straightforward. What we do now, to attempt to do this with going through the origin, is something like that. So I'm still following the ground rules. The curve goes through the origin as much as possible. My iPad pen I wasn't very accurate with, but you can see what I'm trying to do. It doesn't touch the x-axis again. And what happens here is only a very small proportion of the same particles can actually overcome activation energy. So this will be a smaller number of particles can overcome EA. Notice that the area under the peaks is actually the same, because you have the same number of particles in each case. So the peak that's colder is a little bit taller, and the peak that's warmer is a little bit shorter, but it goes further above the x-axis. So it's very important to remember that the area under the curve remains unchanged. Okay, so now what we can do is try an exam question. So what I've decided to do is stick with a longer answer exam question, and I should actually say 7 marks. I'm just going to change that. Here we go. And it says, in your answer you should organise your answer and use the correct technical terms. So the first thing to do is to look at what they actually are asking us in the question, as I always say. And if we do that, we can see that really what they want us to do is explain how a catalyst increases the rate of reaction. So just saying that it makes the reaction go faster is clearly not going to get 7 marks. If we now have a look at how they want us to do that, they want us to do it using an enthalpy profile diagram and a Boltzmann distribution. So I would suggest doing this by splitting your answer into 2 halves. One half is the enthalpy profile diagram. So we've done that already earlier in the clip. So that's simply a case of doing your axes. Oops, make this slightly better. Labeling them like so. And then we can put in the reactants and products. Like that. So now I'm going to switch colours slightly just to make it a bit easier. So you start off by doing your normal uncatalyzed enthalpy profile diagram, or reaction curve, and I'm going to do a different colour and do the catalyzed one. So I'm going to have two activation energies. It doesn't matter where you put the arrow, as long as it's actually in the right place. And what I can do is I can call the catalyzed version EC and the uncatalyzed version EA. So because I'm a little bit short of space here, I placed them outside the curve, but ideally you'd put them inside the curve, so it's absolutely crystal clear to the examiner what you mean. The next thing to do is to put in the delta H. Now the delta H here is exothermic or negative, so the arrow should point from the reactants down to the energy that the products are at, like so. I've seen some people before put it in as negative just to try and reinforce what they're saying. Don't do that, because that's actually implying that it points up. So you don't have to bother with that. Just leave it as delta H, like that. Okay. The next thing to do is to do our Boltzmann distribution. And the Boltzmann distribution I'm going to do on the right hand side. Again, we have a set of axes, like so. Need to be labelled. That will be sufficient, and we make sure that our curve goes to the origin, like so, and it sort of levels off a bit like that. That's fine. So now what we have to do is to put the activation energy, can do it there, and then the extra activation energy we could write it like this, and you can highlight the additional molecules that can react with the additional molecules that can react with the catalyst actually added. So how you might label that would be something like this. We go about marking this. So first of all, you have your curves and your enthalpy profile diagram done. So those are the 3 points that will get you marks there. You'll also need to say that the activation energy is correctly showed in that way. With the Boltzmann diagram, you need to have correct drawing of the Boltzmann diagram itself. You'll also need to say there are more molecules with energy above the activation energy with the catalyst. I'm just going to add one more thing that I think I missed out earlier, the idea of more effective collisions due to this. So let's see where we can give the marks. You have one for this point here, so 4 for your enthalpy profile diagram, 1 about the kinetic energy, 1 about more effective collisions as well, and the correct overall drawing of the Boltzmann graph using the areas we talked about before. Okay, so I hope this has been a useful exercise for you, this clip. Obviously, any more questions you might have, please get in touch with your teacher, go to a subject extension, or have a look in the textbook. But thanks for listening, and all the best. Thank you. Bye.